Oof. This is perhaps an example, the only example that often comes up where it's a little bit different. If you're given the dreaded carousel, the complication here is that weight always acts downwards. Weight is not always it doesn't consistently play the role of the centripetal force. Sometimes it acts in alignment with it, for example, at A. Sometimes it acts against its interests at C. What needs to take up the slack then and counteract the weight and then go some more is the tension. So at point C, the tension is going to have to be really big because not only does it need to support the weight of the carriage, but it also needs to provide some centripetal acceleration. But at A, the tension will ease off. It doesn't need to do so much pulling. It might still contribute a little bit, but as long as the vector sum of the forces on each carriage is constant and it's constantly equal to the required centripetal force, fine. So this point in the green box, the magnitude of the resultant centripetal force is constant, but its components vary. Okay, so at A, the normal concept force, the tension, acts in the same direction as the weight. So I've labeled it as T here, but let's change it to R. Because I was assuming the sort of spokes were providing tension, but instead it looks like it's on some sort of fixed disc, and that's what's providing the weight. Fine, I don't mind. So at A, R plus mg are going to be equal to our centripetal force. Nice. As a result, R doesn't need to be very big. It can be quite small. At B, R acts perpendicular to the weight, so it doesn't really have an effect. Or the weight doesn't have an effect. So R is exactly equal to the centripetal force because the weight is busy, acting perpendicular to it. At C, I'm afraid R has to act against the weight. R minus mg is equal to Fc. The size of Fc is constant. So what changes is the magnitude of R. R is a reactionary force in this instance. It changes its size as the carriage goes around the wheel. Magic. Okie dokie. How we do for time? Let's push on a little bit faster. I think there's too much dilly-dallying about technical difficulties. Inside a washing machine, a sock spins around in a vertical circle stuck to the inside drum. Explain how the normal reaction force acting on the sock varies as it completes the circle. 3 marks, we want 3 different points. Very similar to the previous slide. We had 3 points, A, B, and C. Maybe that's a good structure to follow. It's only in bullet points, so don't write fancy sentences. But each point we keep it focused on the normal reaction force. We are explaining, that's our command word, but keep it specific to the normal reaction force. We don't necessarily need to know the weight. So the normal reaction force always points perpendicular to the surface of the drum towards the center of the drum. Good, that's a general description. The magnitude of the normal force is maximum at the bottom of the drum, as it has to oppose the weight and provide centripetal force. And the magnitude is at a minimum at the top because it acts, it provides only part of the centripetal force as the weight helps